Okay. So I'm starting, right?
Yeah.
Yeah. Okay. So today we are going to discuss about the basics of density functional theory. So density functional theory, it comes under electron structure theory. So we will see first that why do we do electron structure theory? So all of us here are chemists. So we do chemistry, right? So basically in chemistry, what happens is that we study reactions, right? And what reactions are is basically either bond making or the bond breaking, right? So and what exactly the bond breaking and bond making is the redistribution of electron density. So these bonds are made up of electrons. So if I want to, understand chemistry, I have to somehow understand electrons. So that's what exactly electron structure theory is about. So it studies the electron in matter. Either, the first approach was given by Schrodinger in 1926, was the wave function based approach. So this electron is a quantum mechanical object, and we study it through quantum mechanics, right? And the very first postulate in quantum mechanics says that all the information of a state is contained in wave function, that is psi. So to understand electron, I need to get wave function. How do I get this wave function? I get wave function by, we have Schrodinger equation. So I'll be writing the time independent Schrodinger equation. So if I want to get my wave function, I should have a Hamiltonian, right? And then I can get my wave function. Now let us look at what my Hamiltonian looks like. So if we see, and I'm talking about this Hamiltonian under Born-Oppenheimer approximation. So this is H electronic basically. So what it will consist of is the kinetic energy. I'm representing kinetic energy by T. So the kinetic energy of electrons and the electron repulsion. Okay, so that is the potential energy, which is written as VEE, electron repulsion. And the other one is the electron nuclear interaction. Okay, so in density functional theory, we call electron nuclear interaction as V external. And why do we call it V external? Is because see, this is all dependent on in this electronic Hamiltonian. Only the electron nuclear interaction part involves nucleus, so we call it external. So that is this V external. Okay. So for a given number of electron, this part, for given number of electron, this part will remain same. Okay, this will not change. The part which will change is the V external. Okay, so if I change the position of my nucleus or the atomic number, because V external depends on that. So my Hamiltonian for a given number of electron depends on V external. Okay, so I'm trying to build a connection here. So I want to get a wave function. To get a wave function, I need to write a Hamiltonian. And as we see here, for a given number of electron, my Hamiltonian is dependent on V external. That means if I change the position of my nucleus, for the V external will change. Therefore, the Hamiltonian will change, and I will get a different wave function. So in quantum mechanics, there exists a one-to-one mapping between, say, if I have psi1. So for that, there is a V external 1. If I have psi2, then I will have a V external. So there exists this one-to-one mapping in quantum mechanics. And it is all developed, it was postulated. So this mapping exists in quantum mechanics. Now in density functional theory, what I want is that I want to use density instead of wave function. Okay. So there are two questions. Why do I want to use density instead of wave function? And the second question is that if I want to use wave function, electron density or probability density instead of wave function, does this kind of mapping exist there also? Okay, so let us answer the first question first, that why do I want to use electron density? Why not wave function? So we see wave function. So wave function is, say for example, if this is my particle and it moves in x direction only, so my wave function will be function of, okay, my wave function will be function of x only. Okay, and if it is moving in, say, y direction also, then it will be function of y also. Similarly, if it moves in z direction, then it will be function of z also. So you see, for one particle,
one question that this Hamiltonian depends on external field. Okay, external field decides. External field decides the whole form of wave function.
For a given number of electrons.
Sorry, for
a given number of electrons.
For a given number of electrons,
Yeah,
that validates only in Born-Oppenheimer, under the Born-Oppenheimer approximation.
Yeah.
So for ground state, it is, I understood it, means there is no problem in understanding.
Yeah.
But for others, means suppose I put any external electric field on top of the nuclear field.
Yeah.
Then is it valid? Means if I put some external field so that it stabilize in a higher electronic state.
No, that won't be. No.
That won't be valid?
No.
Okay.
So,
I think people use, means I am asking that question in the connection of time dependent DFT. So there people use some kind of similar approximation.
Yeah. But I here I am discussing about just not the time dependent one.
Not the time dependent, yes. But I am I wanted to connect means how far we can make this approximation. So there also I think means if we use the similar kind of approximation, there will be means lots of saviors for us, means in terms of calculation.
Yeah.
So it saves us lots of means complicated things. So this Runge-Gross theorem. There. Okay, there is one. This
actually,
is one
so I'm not that aware about the time dependent density functional theory. So here, like I understand that you want to connect, but I am discussing about the density functional theory, which is like for the ground state only.
Yeah. But these kind of things means is a savior. Mathematically, it simplifies many complications. Means if you don't approximate like this, means density functional theory never comes, I think. Never in the field. Okay.
Yeah, thank you. So the wave function, so for one particle, the wave function is dependent on like 3 coordinates. So if I have n, it will be dependent on 3n coordinates. So for many body, like if I have like a large number of particles, so to handle the wave function is very difficult. Whereas in electron density, it is dependent on just 3 coordinates. Now you can ask me that how the probability density is dependent on 3 coordinates, because I get my probability as psi into psi star, right? So how is it dependent on just three coordinates? So what we use is reduced density. So what is reduced density is basically that that the electron density is written as psi, so this x1, x2, x3 up to xn. So this is pi, actually pi is Rn sigma. So n psi star pi 1, pi chi3 up to chi n. So if I integrate it over chi2 to chi n, and then sum over all sigma. So what I'll be left with just R. This is R1. Okay, so what I'm doing is this information is still in the electron density, but I am integrating it with respect to all other coordinates, and I'm just left with this one. So this is known as reduced density. So that's what we use. Okay, so now the motivation that why we use electron density instead of wave function is clear. Now the second question, that does this mapping that rho R1 corresponds to rho 2 R, and there exists like V external R1 and V external R. So does this kind of mapping exist or not? So the answer is that yes, it does, and it was given by first Hornberg and Kohn, first theorem, which was in 1964. Okay. So I'll just prove the first Hornberg and Kohn theorem, which is very simple, and it is by simple contradiction. So it is a very simple proof. I'll just prove it. I'm writing it as HK1. Okay, so this is for ground state and for non-degenerate. And there is something called V representability, which I'll explain later. So as Hornberg said that for every V external, there exists a unique electron density, right? There is a one-to-one mapping. So if I vary my V external, then I'll get a new electron density. So we'll assume here that I'm considering two V externals. V external 1 or V external and V external prime. Okay, and these are not equal, and they give me the same electron density, say rho R. Okay, so if I have two different V external, so I will have a Hamiltonian for it. Okay, and then I will get a Hamiltonian for it and a wave function for it, and the ground state energy for it I can calculate E0. Similarly for this one also, I will have Hamiltonian H prime, a wave function S prime, sorry, psi prime, and E0 prime. So, and these are not equal. And I'm saying that both of these are giving me the same electron density. That's what I'm doing here. Now, how do we calculate the energy? So the energy is calculated as E as a functional of rho is given as psi H psi. Okay. Similarly for this one, E psi prime H prime psi prime. So this is the true energy, ground state energy, which I'm calculating, as we know that that's how we calculate it. Okay, so first of all, I'll just try to solve this one part, that how I can write it. So as you can see that H can be written like this. Okay, so I'm putting the value of H here. So this is my psi T plus
Priya?
yeah.
We are just assuming like these two different Hamiltonians, like these two different V externals are giving us same density. We are assuming it. Oh,
Yeah.
okay.
We'll prove it by contradiction. Like it's otherwise, right? That if we have two different V external, it should give me two different electron density. Electron density.
Oh,
Yeah.
okay.
So I'm assuming that later I'll prove it wrong. That's
Okay.
so TVE psi. Okay. Plus I can write this part as psi V external psi. This one I can write as a functional of electron density. So this one I can write as rho r V external r d. Okay, so that's how I can write my this part. This is also how I can write. Okay, I'm going to use it. That's why I've written it down. So now let us do one thing, that I'm taking this Hamiltonian and I'll use this wave function psi prime as its trial wave function. Okay, so what will happen using the variational variation principle, that if I'll use psi prime as my trial wave function for this Hamiltonian, so the energy which I will get will be always greater than, this E0. So E0, it will be less than whatever energy I'll be getting. So say this is psi prime I'm using, this one as the trial, and this one is my Hamiltonian. So this I will get. Okay. Now I'm writing it as H prime, like I'm adding and subtracting H prime in this, which is simple. Okay, so I can write it as, E0. Is it visible or is it very small?
Yeah, visible.
It's visible.
So,
But make it large.
okay. So this is my E0, and I can write it as psi prime, H prime, psi prime, plus psi prime, H minus H prime, psi prime. Okay, now what is this? This is this one, right? This is, so I will substitute this. This is E naught prime. So this is one equation we get. Okay. And similarly, just like the way we did it here, and I can write this part as E0. So this part I am writing. So if you see for H and H prime, this part will be same. Okay, so this will get cancelled out. And only part which will be different, for H, V external is this one. For H prime, V external is this one. So I will get it here as like plus rho r V external minus V external r minus V external r prime d3r. Okay, so this is my one equation. Similarly, what I can do is that I can use this Hamiltonian and use psi as its trial wave function, like opposite I'm doing now. So similarly, I'll get an equation like the way I have written here. It will be like E naught prime will be less than psi if I use psi as my trial wave function, and H prime psi. I'll do the similar thing. I'll plus add and subtract H in this. So I will get an equation. I'll directly write the equation because it is very simple, almost similar. So I'll get an equation which will be E naught prime is less than E naught minus, there will be a minus sign, rho r V external r prime minus V external r d3r. Okay. And if I add these two equations, you see, if I add these two equations, this part will get cancelled out, and I'll be left with, what I'll be left with will be that E0 plus E0 prime is less than E0 plus E0 prime. And this is not true, right? So hence our assumption was wrong, that for two V externals which are not same, which are different, I'll get different electron density. Okay.
Priya,
Uh,
just explain once how we can write the V external as an integration over rho r.
So if so what is my V external is psi V external psi. So this is basically integration of V external as a function of psi into psi star. Okay, I'll write it. This is function of my function of these coordinates. Okay. And this V external is dependent on my Z, and that is divided by 1 by the internuclear distance. So I can write simply as V external, and this I can write as rho r. Like if I integrate it over all the coordinates.
Yeah, right.
So this is the first Hornberg and Kohn theorem, which we
So what is the first message? Like, what is the message from the Hohenberg-Kohn first theorem? The
So,
central message.
so the first message is that, like, as in quantum mechanics, that there exists a one-to-one mapping between wave function and V external. There exists a mapping between electron probability density and V external also. But there is one problem, that is that I said, that is V representability. What does that mean is that I'll explain it. So for example, if I have a V external, okay, the message is that if I change my V external, I'll get a different electron density. That is the message. Like for every V external, there exists a unique electron density. That's what it is trying to say. Okay. But the one thing is that I'm saying that for every V external, there exists one electron density, okay, unique electron density. But I don't know the conditions that say if I have an electron density, okay, and if it integrates over, if I integrate it over all the space, then I get the number of electrons and number of the particles. So if I have an electron density, then I cannot tell whether it is coming from a V external or not. That I can't tell. Those conditions are not known. Like whether given an electron density that is coming from a V external or not, like whether that V external is basically that internuclear interaction, right? Whether it belongs to an atomic or a molecular system or not, that I can't tell. Those conditions are not known. So what happens is that since this condition is not known, that if I'm given an electron density, how I will find that whether it belongs to a V external or not. So what happens is that this is known as V representability problem.
Means can I understood that thing in this way that the back trace is not possible? Means the external to row is means
Yeah.
for a particular external there is a particular row, but for a particular row means the vice versa is not true always in general.
Yeah, that is true, but it's not that obvious. Like
Not that
you can
obvious.
find it.
That row we can make it in other ways also. The same kind of electron density. It is possible that we can means in explaining DFT it will be clear means later on that how is that's why the approximation in the DFT means those are so flexible.
Yeah.
Actually, I have just a concern. So actually, I think this is one-to-one mapping, right? Because from V external to rower. So from a unique V external, we get an unique rower, and from a unique rower, we get an unique V external.
Opposite way is not means that
No,
is
it
the
is
point.
true.
Yeah,
It is
but
not
if I
obvious
have-
that we cannot find it.
Yeah,
Whether
it is
it's coming
true.
from it or not.
The mapping is true, but if I have an a density, let's say rower, then I cannot I wouldn't know how from which V external this row is coming from, right? So the mapping is itself true, but we cannot analytically know or we cannot predict which V external the rower is coming from.
Yeah. The conditions are not known, but the mapping is true.
Yeah, mapping is
mapping
true.
is
Yeah.
correct.
Yeah.
Yes.
So what we do is that, so this is known as V representability problem. So what we do is that we know that, okay, this electron density is, see, we are not using wave function, but this electron density is coming from a wave function. We know that, okay? So if that wave function is antisymmetric, if that wave function is valid, so I know that this mapping exists in quantum mechanics. Like this is postulated, so there is no problem here. So if I somehow I can go that if I can find that this electron density is coming from a valid wave function. Okay, so this is known as a weaker condition and known as N representability. So if not this way, then if I can get those conditions that it is coming from a valid wave function, then this map is completed like this way. So there are three conditions and which are given by mathematicians. So the first one is very obvious that rho r should be greater than 0 or equal to, and the integration of rho r d3r should give me n number of electrons. And the third one is for the kinetic energy. It's not exactly the kinetic energy, but it is proved by mathematicians and it is used as such that the integration of rho r where d3r should be less than infinity. Like the kinetic energy should be finite. So if any electron density follows these conditions, then I will say, okay, I'll take it. Like I can take and then I'll see what happened. So this is a weaker condition. So yeah, this is known as N representability. Now, as the Hornberg and Kohn theorem was for
Priya,
non-definite case.
where there is del to the power half and rho to the power rho square in the third condition.
This one. Actually, the kinetic energy, like the kinetic energy is Laplacian of this, like psi into Laplacian and psi star. So this is not exactly the kinetic energy, but as I told that it was proved by mathematician earlier, like now it was proved in some other context, but they said that they can use this condition to say that if this is less than infinity, then we can say that this is used for the kinetic energy, like kinetic energy is finite.
Okay.
Yeah, so the Hornberg and Kohn theorem was for the non-degenerate and V representable. Okay, But here we said that if there is not V representability, then N representability will do. And so there was another theorem which was given by Levy constraint search formulation, and it was given for N representable and degenerate case, which are not proof, but yeah, it was extended for N representable and the degenerate cases, but for ground state only. Now, okay, if now we know that we know the condition for electron density, that if it follows these three conditions, we can take it. But how do we find electron density? So it is similar as in quantum mechanics, that is by the variational minimization. That so that is Hornberg and Cohn's second theorem, which says that that the true ground state energy is functional of true electron density, and any other trial density will give me energy either equal to or greater than this. So basically it said that it also follows variational minimization. Okay. Now, if it follows the variational minimization principle, then it says that the ground state density should satisfy the stationary principle. That means that if I vary this E as a function of rho, it should give me 0. Like it should not vary, okay, because this is the minimum. But this electron density cannot be anything. There is a constraint in it. So there was a constraint. So mu rho r d3r. This mu is the Lagrange multiplier. Okay, so this is the equation. So now if I do the functional derivative with respect to it, so it gives me E naught rho del rho is equals to mu. Okay, so this is known as Euler equation. And this equation is the governing equation for density functional theory. So actually, if we want to do the original density functional theory, then one should solve this equation and do the DFT. So it is like the governing equation, Euler equation, as there is Schrodinger equation in quantum mechanics. So this one is the governing equation. Now there is one problem. If I want to do functional derivative with respect to rho, then I should know that how to write my E, that is the total energy, as a functional of rho. Okay, what I mean to say is that I should know that how to write my total energy as a functional of rho. That means I should know that how to write my kinetic energy as a functional of rho and the potential energy as a functional of rho. Okay, now here the problem starts. So this form is not known. It's unknown. This is partly unknown. So this consists of electron-electron repulsion. There is an electrostatic part, which is known as classical part. So classical electron-electron repulsion, I will write by J rho. That is okay, that is known. Plus, to that electron-electron repulsion part, there is some quantum mechanical non-classical part also known as exchange and correlation. So I will write it as VXC. This is not known, unknown. Okay. And there is obviously this V external part, that is okay. Okay, so these two things are not known. Now, as you might be aware that there are a lot of exchange correlation functions. So it's still pretty much somewhere has done progresses, because there are a lot of exchange correlation functionals already there. But this part, writing kinetic energy as a functional of rho is not known. Okay, and writing this part explicitly as a functional of rho, solving the Euler equation, is known as orbital free density functional theory. So that's what we do, and is actually the original DFT. This is one way that I write it in form of this. I solve the Euler equation. The other thing, the other option was that if I can't write anything, then I have to approximate it, right? That's what Kohn Sham did. So Kohn and Sham, they bypass this problem.
So what is orbital free DFT?
So I'll explain. I think it will be more clear because it include orbital. So it comes from, because in Kohn Sham they uses orbital,
Yeah,
but in orbital free it is not orbital. We will use rho, means the total electron density, not the orbital one, which is used in
yes.
Kohn.
So you start with electron density form, right? But to get a rho, you have to use some kind of orbital, right?
To give it a
To get a electron density form, rho. So where do you find rho? To get a electron density form, you have to use some kind of orbital, like lowest level orbital, like some kind of thing.
Okay. So if I can write my total energy as a functional of rho,
yeah.
Okay, and if I do the functional, like if I do the variational minimization, wouldn't I get the electron density then?
Okay, so you don't have to know the explicit form of rho. Just if you know just kinetic energy as a function of rho, then you can obviously.
Like I have to write it in as a functional of rho, as in like I say that f is function of x, so I have to write something as a function of x. I don't need to know what is x exactly. Like that, like you have to write it in a functional form of. Then you will do variational minimization, and then you can find the electron density.
Yes.
One connected question, that this without the picture of orbital, means how could I get the functional form? This this kinetic energy also, and exchange correlation is means I could not imagine at all.
Yeah,
how could I get?
This is, I think, partly because we have imagined it the other way only, because we have seen the orbital picture first. And now we cannot imagine. So basically what happens is that you are saying it correctly, that if orbitals are not there, that means that the Pauli exclusion principle will not be followed. What I mean is that in Kohn Sham, we are using orbital, that is, we are using Slater determinant, right? So that is already followed. And when I'm saying that this is difficult, this is unknown, why I'm saying it? This is the reason that I can get, there have been approximation, like there is for homogeneous electron gas they have done, for hydrogenic, that is von Weizsäcker part, they have done. But our atomic systems are like homogeneous electron gas is where there is this uniform potential, right? And the von Weizsäcker is like there is this nuclear and one electron, hydrogen-like. So these are the two extreme, but our atoms are somewhere in between, right? So that is exactly the problem. When we try to find any T as a functional of rho, so what happens is that it does not follow the Pauli exclusion principle. So that is the challenge, that we have to find such a kinetic energy functional that follows my Pauli exclusion principle. Whereas in Kohn Sham, it is already by default put it in, like they're using orbitals. So they will follow, like Slater determinant they're using, so they will follow Pauli exclusion principle, and that's why it's very exact also.
Yes, without means are there such approximated form where without using orbital, means they
there are there are
Pauli exclusion principle automatically
they are not followed. Yeah, so somehow in here also we have to do some, we have to do some approximation, because it's very difficult to get. Otherwise, you're correctly saying that it's difficult to imagine, but yeah, but this is not impossible, because this was what was originally proposed, and this is what DFT is about. It's like it's
This is
difficult.
like every theoretician's dream.
Huh?
This is like the holy grail of electron structure theory. So every
It's like a
theoretician's
theory, yes. But main difficulty is that electron-electron correlation
Mhm.
is very much quantum mechanical,
Hmm.
totally quantum mechanical. So to model this whole correlation in one one row functional is
Yeah,
Hmm.
that's why there are billions of functionals.
Yeah.
this is in the cone sum picture, orbital picture.
Hmm.
Orbital free picture is if there are some review or something, then
Hmm.
you might share.
Yeah, I'll sure.
Okay.
So, but as you said, no, like if the orbital picture, like if it comes true, then what will happen? So in Concham, we are using orbitals, right? So it depends on our number of particles, because we have to solve these n-coupled linear differential equation.
Mhm.
Okay, I think I should write first, then we
Yeah,
will
yeah,
discuss.
yeah. Then we can discuss. Yeah.
So yeah, what Concham did was that it bypassed that problem. Okay. So, and what does it mean that how did it bypass this problem? So what he did. So what Concham did was that, so for example, we have a real system. In real system, what happens is that, for example, this is my real system. Okay. So there are nucleus, there are electrons, and yeah, obviously they are interacting. So they are interacting with each other. Okay. So this is my real system, where real and interacting. Okay. What Concham did was, because if they are interacting, then it's very difficult to write the kinetic energy as a functional of rho. So what he did was that he mimicked this system. He said that I will take a system which will give me the same density, okay, as of the real system. But I'll not take real particles. These will be fictitious particles. Okay, these are fictitious. These are not real. So these are fictitious particles. They are non-interacting. Okay. But there is a condition that the electron density would be same as that of real. Okay. If they are not interacting, then what happens is that it will feel mean field potential. Okay. So this one is feeling potential from every other one. Similarly, this one is feeling from every other one. So it will feel a V effective. Okay, this is mean field potential. Now, he considered each particle as this quantum mechanical particle, they are not interacting. So what he did was that now the kinetic energy, so if I write this as my total kinetic energy, will be sum of individual kinetic energy. Okay, because these are not interacting now. So he can write it as sum of these. That's what he approximated. But this is not really the kinetic energy, right? This is not the true kinetic energy. Like the particles or the electron will have a different kinetic energy when they will interact than when they are not interacting. So this was his approximation. So he sort of bypassed this problem that I cannot write the T as a function of rho for interacting particles. So what I'll do is that I'll consider them non-interacting, and then I'll write it as sum of all of these. Okay, similarly, the total electron density was also written as sum of the individual, okay, of the individual particles. Okay, so in Concham, what happens is that we get in Concham. So in Concham, I'll write this equation. So this is the Concham equation 1 by del square plus V effective function of R or rho maybe it is the function of rho R. Rho R. Phi I equals to Pi by R. Okay. So this is the Kohn-Sham equation. So these phi I are the number of particles which are there. So the total density is sum of that, and the total energy is also the sum of these eigen values which will come. Okay. Now this V effective part. Now see what this V effective part is full of, right? So this has, as I told, J rho, which means the electrostatic electron repulsion part, which is the classical part, plus it has V exchange as a function of rho, plus it has this V external part, plus there is this is not the true kinetic energy, right? So there is some kinetic energy correction which is also there, T correction I will write, and this T correction is also dumped into this exchange correlation. And this is the reason that we are not able to find the exact exchange correlation functional. Like finding exchange correlation functional is a hit and trial. Like people try different things, and because there is no systematic way to do it. Okay. It has exchange correlation, T correction. We don't know how much of it is coming from which part, exchange correlation correction. T correction is even not like, they don't talk about it also. So that's why it's like for different system, we use different exchange correlation functionals. So there are a lot of exchange correlation functionals in available. So I'll write those. So I think all of you must have seen this also, the Jacob ladder. So there are exchange correlation functional. It says that if you go up the ladder, the computational cost and the accuracy increases, but it is not always the case that accuracy will increase. But yeah, so for the exchange correlation part, exchange correlation. So the first one in the ladder is the LDA, that is the local density approximation. So the local density approximation is basically like, if you consider the local density approximation is just, you are considering the electron density. Okay, that means that it is like homogeneous electron gas, that at every position you are just taking electron density. Okay, then comes GGA, which is generalized gradient approximation, GGA. So to increase the accuracy, apart from using electron density, they have used the gradient also. Then meta GGA. So in meta GGA, they used rho R, gradient of rho R, and Laplacian of rho R. So they use the Laplacian also. Then comes hybrid functionals, and you might know hybrid. So what does hybrid means? Hybrid means that it is a mixture, or it is a hybrid of two things. So the famous example of it is B3 lib. We all of us use it. So what they have done in hybrid is that, so in Hartree-Fock, there is this there is an expression for exchange part. So what they have done is that they have taken their exchange expression, but they are using Kohn-Sham orbitals in it. That means that there is a hybridization. So they have taken formula from Hartree-Fock exchange part, but they are using Kohn-Sham orbitals into it. So as you can see that there is not a systematic way. They are trying it in different ways. Otherwise, this hybrid function does not make much sense. Like if you are using Kohn-Sham DFT, then why are you using something from Hartree-Fock just to make your expression? So why they are doing it? Because to get the same electron density, they have to model the V effective potential. They have to model. They have to get the correct V effective. So that's why they keep on trying different things until and unless they don't get it correct. Yeah. So that's it from my side. Hello? Hello?
Yeah, we are live.
Yeah. So yeah, that's what I wanted to discuss. That yeah, okay, I can say the drawbacks of Kohn-Sham DFT also. So as you can see that in that they approximate the kinetic energy part, and they have put the kinetic energy correction also in exchange correlation. Plus these particles are fictitious. Their Kohn-Sham orbitals does not have any sense. They like they're trying to find that what does Kohn-Sham orbital means, but they're not real. So there is not much sense to it. Plus the computational cost increases as the number of particles or the number of electrons increases. Yeah. And obviously there is no systematic way to find out the exchange correlation part. So this is basically hit and trial. And yeah, so apart from the drawbacks also, this is an exact theory, like it gives results. So I'm not saying that we should not use it, but yeah, I think we should be aware about like what we are using. Yes.
Yeah, in principle, it is exact theory,
It is correct.
but in practice, it is too much approximated.
Mhm.
One means one functional result. If we use one functional for the same system, other functional can give drastically different.
And that is for a very small system also.
Yeah, drastically different means qualitatively different result also. That is more confusing. So means our ideal means I want to comment that means our ideal scenario is to use these Hartree-Fock means post-Hartree-Fock methods that are more accurate, but that are too much costly. That's why we bypass by this DFT, density function theory. But here we have to put the price. Okay, so for the inaccuracy. So there is a nice article. I think means the quantum mechanics and DFT people actually predict the 10 years. What is the fate after 10 years of this theory? Means they will, I think, saturate with a benchmarking, which is the best and what is the then we need probably means in the fundamental now what all the people are doing in this field, they using the means basic fundamental law are same, means the framework is same. They are putting different exchange correlation in the same framework, means this non-interacting, and but they did not think about this means putting some modification of that framework. So that is means after the Kohn-Sham means nobody thought in that direction. So I think that is not so easy. Means that is
actually if you see that from so this idea of the original idea of DFT is like very old, right? But after Kohn-Sham DFT, people stopped working on the original idea.
Yes. That's what they also They
But
also mentioned in that perspective article.
So if you see in the last couple of years, from 2020s, people are coming back on orbital free DFT. Like there is little more interest, but yeah, it is again very difficult.
Very difficult
approximation. Yeah.
Okay, so I have one
question. Yeah, I have one doubt. Okay, so Deep, you go ahead.
No, you can go ahead. I can ask.
Okay. So I didn't understand this part, that from one particular V external, we get a particular rho density. Then this backtrace or this reverse, like what you explained, that from a particular rho we cannot get this origin of V external or the fixed or the same V external.
Like, see, the mapping is correct. That for a V external, there is electron density, unique electron density. For a unique electron density, there is a V external. But see, if you want to check something, that if I give you an electron density, say that is giving me, if I integrate it over all the space, then it is giving me some n number of electron, like it is a valid electron density, okay, symmetric and all of that. But if you have to check that from which V external it is coming, you cannot check. Like in quantum mechanics, what we do is that we solve the like we write Hamiltonian, we know what is V external, and then we solve wave function. So we know that from where this wave function is coming.
But from which V external means there is only one V external, this
There
electron
is
and this
only one V
nucleus.
external. See, I'm saying that it could be coming from something else also. V external
Okay.
here, I mean that it should be for an atomic system or a molecular system. So for example, if you have e to the power minus alpha x square, and like for the harmonic oscillator, if you have wave function, you can find out the electron density, but does that electron density correspond to some atom or molecule, like some internuclear part or not? The condition are not known, like how you will check,
Okay.
that is not known.
Okay. So we can get the same V external back, but we do not know the this origin.
Condition, like how to go about it.
Okay.
Hmm.
Okay. Yeah, Subhadeep.
Yeah, I almost forgot the question. So in orbital to DFT, so let's say you write the kinetic energy functional as in functional of rho. Let's say you have the form. Okay. You solve the Euler equation, like functional, you do the functional derivative, do the variational minimization, and you get a ground state energy as a function of rho, right? Now you solve the energy states. Getting this means you are solving the energy states of a particular molecule or let's say system, right? Ground state energy. But in orbital free DFT, by doing this, you cannot get the pictorial representation of a molecule, right? In how the different atoms are, how the electron densities are, because you are not getting any functional form of rho as a function of coordinates. So you cannot get any pictorial representation of molecule. Am I correct?
What, like I have discussed this earlier, not here, but yeah. But so like what happens is that if you have so for example, if you have two molecules, okay, if you have two molecules, then and if they are reacting, so this molecule is a density, right? There will be a density for it. So when they will react, so they will have this combined electron density. So it says that you can see that how that electron density is changing. This entire electron density is changing.
Yeah.
No,
but in normal DFT, when you do DFT, we can for let's say in the dynamic space also, let's say at each time you get the wave function and you can plot those and you can get how the molecule is behaving, how the electrons are behaving, like this. No? You can get the pictorial representation of orbital. Orbital means the creation of orbital is to get the pictorial representation of molecule. But in orbital free DFT, you cannot get that, right?
Now, orbital means we want to see how each electron behaves. Means we are accustomed with the Bohr picture that each electron have a different means a particular orbital, a constant in the orbital.
That's the purpose of orbital.
Yeah. But in the molecular, suppose means you run a quantum chemical calculation, you get an electron density, okay.
Yeah.
Then means from the wave function based calculation or anyhow, you get some final electron density for a molecule, okay. So this is your rho. Okay, you can see all the polarization and all the molecular properties.
Then I can plot the electron density and I can see how the electrons are behaving. I can in orbital picture that is clear. But in orbital free DFT, in your case, we cannot get a functional form of rho. Right? We cannot get a functional form of rho as a function of different coordinates.
See, okay. So, see, if, like, for example, as I
Mhm.
discussed, that how do we get this reduced electron density? Okay, what you are saying is that, okay, I don't have rho written as a function of each,
Yes,
uh,
yes.
right? Yeah, but as I told it earlier also, so when I'm saying that I'm using 3 coordinates, or I'm
Mhm.
using the reduced electron density, that means that all the information that was there is still there. It will be, see, I think you are talking specifically about the plotting, but if you see the logic, that is that in wave function, if you have, if like some, it is function of r1, r2, r3 up to rn. So what it is saying is that if r1 is here, then r2 is there, r3 is there, rn, like it is giving you this, no, like the entire information, how the system is. So I
Mhm.
got my electron density from the wave function only. The only thing is that I have integrated that part. So that information is still there. It is just dumped, like it is not, it has not gone anywhere.
Okay.
That's what I'm saying, that if it depends on 3 coordinate, but that does not mean that it does not contain any information about the system. Then how, if it does not, then why would we even use electron density, you know?
Yeah.
Yeah, means if you can imagine, like, means this back trace way, means you have a very accurate from quantum chemical calculation, you have electron density of a molecule very accurately. So after that, you can construct you can visualize the where electron density is higher in space, where electron density is lower in space. So you can backtrace all the things. Okay, means but the direct, without those calculation, means direct approximate the electron density first hand, it is very difficult. It is not possible. That is the orbital free sense of orbital free.
Yeah.
I think this is very nice.
Yeah, it's a nice talk.
Yeah, very nice talk, and yeah,
Thank you.
you you ended with very perfect timing. Means I don't remember that. Me, for my case also, it takes means near about 2 hours, and okay, with this perfect timing, this you nicely presented.
Thank you so much.
Okay, we will discuss for the next talk after I stop.
So there are no other questions.